Okay, let's go over this quiz. So number one said how much work is done by the boy pulling his sister 30 meters in a wagon. So just got work is equal to force times distance, cosine theta. So he's pulling at a force of 50 newtons, a distance of 30 meters, but the direction of the force is at an angle, so that is why it is cosine 30 degrees. So when you calculate that, you should get around 1.3 times 10 to the third joules. All right, number two says compare the kinetic energy of a 25,000 kilogram truck moving at 120 kilometers per hour with that of a 50 kilogram astronaut in orbit moving at 37,500 kilometers per hour. So we're going to see which one is higher, I guess. So first off, though, I don't like these units. Got to convert, which should be around 33.3 meters per second. This next one is 37,500. So when I do this one, I get about 10,416 meters per second. Seemed like most of you did pretty good on the conversion, and I'm not sure if it was that there were different things, but this first one is the 25,000 kilogram truck is going 33.3 meters per second squared. So you got to make sure and square that. Remember order of operations, so when you do that first one, you get around 1.4 times 10 to the 7th joules. And for the second one, the astronaut, you kind of do all of this stuff, should get about 2.7 times 10 to the 9th joules. So if you compared that, like saying 2.7 times 10 to the 9th divided by 1.4 times 10 to the 7th, that should show you that the astronaut is moving about 200 times more. So honestly, if you did the kinetic energy calculations, I was good with that. Okay, this next one says that we have a 100-gram toy car propelled by a compressed spring that starts it moving. The car follows a curved track. What is the final speed of the car if its initial speed is 2 meters per second and it coasts up the frictionless slope, gaining 0.18 meters in altitude? So this was before we had done springs, but you didn't need to do anything with the spring equation. So there was no spring constant given or anything like that. You do, however, need to do the energy principle equation. So we are actually trying to find the final speed. So that means that we definitely need to be looking at that. Does it have initial speed? It does, so we have that. It goes up. It's kind of like doing this, goes up. So right here, it has no potential energy. When it gets to here, it was at 0.18 meters. Okay, so we have all three of these things that we have to consider. So if we write the long version of those, I don't know why I put equals, so it's supposed to be plus 1/2 mass times velocity squared. Remember, we're solving for the velocity here, so subtract those over, multiply by 2, but that multiplies it by all of that. So then that half cancels, and you have 2 mgy then. Divide by mass. Mass cancels out on both sides. Do the square root. Okay, so you have your initial velocity, which is this 2 minus 2 times 9.8 times 0.18. Sorry that I didn't have enough room. So, oh, and that's the square root. So once you do the square root of that, you get 0.687 meters per second. All right, number 4. Number 4 says that you've got a 50-gram ball on a pendulum swinging back and forth, and it reaches a height of 0.5 meters. What is the velocity of the ball at the lowest point? So on a pendulum, the velocity at the lowest point is really its fastest velocity. So this is also solving for Vmax. Well, hold on a second. Let me write this different. So we're doing the energy principle again. Let's think about it. If it's a pendulum, that means that it's, like, let's say here's a ring stand. The ball is up here. And this is 0.5 meters. At this point right here, does it have any velocity? For that split moment, its initial velocity is nothing. Does it have potential energy? Yes. We're solving for the velocity when it's here at the lowest point. And at the lowest point, it has no potential energy. So here we're just these two. It's kind of like the number 3, only it doesn't have as much really. So when you go through and you solve this, that cancels, divide by mass, that cancels. So you end up with this equation. So the square root of 2 times 9.8 times that 0.5 meters, which ends up giving you this 3.13 meters per second. Okay. Another type of energy equation or principle equation is where we have, it's asking how high a hill can a car coast up if work done by friction is negligible and its initial speed is 110 kilometers per hour. So, of course, it doesn't like kilometers. Once you did put it in meters per second. So when you go through and do that, you should get 30.6 meters per second. It has no friction involved. So if we were setting it up like this again, and this is initial, and this is final. Okay. Does it have initial speed? Yes. Does it have initial potential energy? No, it does not say that it's already at a certain height. It wants to know how high it can coast up. So that means how high before it stops. So if it stops, then that's 0. So it's the same sort of situation as number 4, except for they're flipped, right? So you have 1/2 mass times velocity squared is equal to mass times gravity times height, or y. And that's what we're solving for. So all you have to do is move these guys around. So you have 1/2 velocity squared over g. So plug those in. 1/2 times this 30.6 meters per second, and then square it, divided by 9.8, and you should get 48 meters. Now for part B, because part A says that friction is negligible. Part B says if in actuality it gets to a height of say 22 meters, how much thermal energy was generated. So now it's wanting you to find basically the frictional amount of energy. So that goes back to this, that non-conservative work. That's what it's wanting you to find, is this. Okay, now, does it have initial speed? It does. Does it have initial potential energy? It does not. Does it have final kinetic energy? Well, if it's coasting up to 22 meters, then this is nothing. And then, does it have final potential energy? It does. It goes to a height of 22 meters. So now we just gotta write these things down. Whoa, sorry. Okay. So if we rearrange this to solve for that non-conservative work, then we've got mass times gravity times height minus 1/2 mass times velocity squared. So now make sure that your units are in kilograms. The height was 22 meters minus 1/2 times 750 times the velocity, which is the same as what we did in part A. Do all of that and you should get 1.89 times 10 to the 5th, and we were solving for work, so what is that measured in? Joules. And that was the quiz. If you guys have any questions about it, let me know.